So in this video, we're going to be looking at finding sequences and series. We're going to look at special sequences, which are called arithmetic sequences, and another special sequence called a geometric sequence. So at the end of the last class period, we were able to get through a little bit of sequences. So let's just recall what a sequence is and go through some examples of those. Okay, so in front of you are some notes. So when you hear the word sequence, as in sequence of events, you're likely to think of something happening first, then second, and so on. In mathematics, the word sequence also deals with outcomes that are first, second, third, and so on. The definition of a sequence is a function whose domain is positive integers. So remember, integers come in from negative infinity, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4. But so these are positive integers, and the range is a set of all real numbers. So let's look at an example of a sequence. So in front of us, we have a sequence called C sub n. C sub n, it gives us the definition of how to find terms of the sequence. It's equal to n squared if n is even, and it's equal to n if n is odd. So to look at the first term, this is when n is equal to 1. 1 is an odd number, so I'm going to use this formula. So C sub 1, plugging in 1 wherever I see an n, is equal to 1. So now looking at C sub 2, 2 is an even number. And so if n is an even number, I'm looking at the formula to plug it in of n squared. But n in this case is 2, so 2 squared is going to give us back 4. So that's the second term of the sequence. The third term of the sequence, C sub 3, n is 3, n is odd, so we're going to get back just 3. So carry on, C sub 4, 4 is an even number. Using the equation for an even number, we're going to plug in 4 for n, and then square it. We get 4 squared, which gives us back 16. C sub 5, 5 is an odd number, so we're using the equation just n, so we get back 5. I just wanted 6 terms, so C sub 6. 6 is an even number, so plugging it in, we get 6 squared, which gives us back 36. So we just got the first 6 terms of this sequence, 1, 4, 3, 16, 5, and 36, but it goes on infinitely using those equations, depending on if your term was even or odd. So in front of us, we're given the sequence, we're given terms of the sequence, and we're trying to find the formula for the sequence. So we're trying to recognize the pattern that's happening in our sequence and come up with an equation for the nth term of that sequence. And so for our first sequence here, we have 1/2, 1/4, 1/8, 1/16, ... So I notice that my numerator is always 1. It's our denominator that's changing. Notice that we have 2, 4, 8, 16, ... So notice that that is 2 to the first power, 2 squared is 4, 2 cubed is 8, 2 to the fourth is 16. So we could rewrite this as 2 to the nth power. And so let's name our nth term, maybe a sub n is equal to 1 over 2 to the nth. So usually when I come up with the formula for the nth term, I will go back and I will make sure that I have the correct sequence. So if I plug in 1, I get 1 over 2 to the first power, which is 1/2, which is the first term of that sequence. Again, if I plug in 2, I get 1 over 2 squared, which is 1/4, second term of the sequence. So it looks like I have the right formula for that sequence. So looking at the sequence below that one, we have the sequence 5, 7, 9, 11, ... So to me, that looks like those are all odd numbers starting with 5 and continuing on. So we want to come up with a sequence, a formula for the nth term. Well, I know to get odd numbers, I am coming up with something like 2 to the n plus 1. So this isn't going to give me my sequence quite yet, but notice that 2 to the n plus 1. If I plug in 1 there, I get 2 times 1 is 2, plus 1 is 3, so that's an odd number. If I plug in 2 there, I get 2 times 2 is 4, plus 1, which is 5. If I plug in 3, I get 2 times 3 is 6, plus that 1 is 7. So I'm almost there. It's just that when I plug in that first one for n, I'm getting a 3, which is not the first term of my sequence. My first term of the sequence is 5. So let's think about this. What if we did 2 to the n plus 3? So let's try it. If I looked at b sub 1, this would be 2 times 1 plus 3. So this here is giving me 2 plus 3, which is 5, which is our first term. Let's just make sure that we're going to get the other terms. So the second term, plugging in 2, we get 2 times n, which is 2 in this case, plus 3. So that gives me 4 plus 3, which is 7. Which notice is my second term of my sequence. So it looks like what I chose to be the formula is correct, but let's continue on just one more time. So b sub 3. So if I plug in 3, where I see n in the formula we came up with, or I came up with, we have 2 times 3, which is 6. 6 plus that 3 gives us 9. So it looks like we came up with a formula for the nth term of that sequence, which I called b sub n. So b sub n is equal to the sequence 2 to the n plus 1. Our next sequence we see is here, -1, 1, -1, 1, ... So notice that I'm always getting 1, but we're alternating with signs. And so if you're alternating with signs, maybe let's call the nth term c sub n. We're going to take -1 and we're going to raise it to a power. So if I raise it to the nth power and I plug in 1 there for the first term, -1 to the first power is -1, which is what we have. If I plug in 2 for the second term, we got -1 quantity squared. But -1 times -1 is +1. So we get that second term. So it's going to alternate back and forth between -1 and +1. If I had started, though, with an even number instead of a negative number, I would have just added up here like a +1. And then when I plugged in 1 there, I would have had -1 squared, which would have been +1. And then I would have started alternating in that from positive to negative. But I started with a negative, so I want to get rid of that +1 there. So the next one, we have the sequence 3, 6, 11, 18, 27, ... So looking at that, and you see what's going on with that sequence. And can we write a formula for that? So looking at the next one, we have 3, 6, 11, 18, and 27. I paused the video for a moment and talked to the class, and they came up with what was going on here. We just need to come up with a formula for that to happen. So notice from the first term 3 to the second term 6, well, I'm adding 3 to 3 to get to 6. From 6 to 11, well, 6 plus 5 is 11. So I'm adding 5 to my term 6 to get to 11. From 11 to 18, notice that I'm adding 7 here to my term before. So 11 plus 7 is 18. If I'm going from 18 to 19, that's not 18 to 19, 18 to 27, we're adding 9 here. So this is actually called a recursive sequence. We're taking a term in our sequence and we're adding something to the previous term. So let me call, let's say, a sub 1 is equal to 3. Well, I know my a sub 2 term is equal to a sub 1 plus 3. And I could write 3, or odd numbers. We talked about being 2 to the n plus 1. 2 to the n plus 1. So that there, just think about this. So this right here is going to be our a sub n plus, well, let's call it a sub n. So a sub n, we're going to take the term right before it. So to write the term right before it, we would do a sub n minus 1 plus 2 to the n plus 1. Would that work? I think we're going to have to do 2. Just pause this. So I'd have a problem with adding with that 2 to the n plus 1. If I subtract 1, I think I'm going to get what I want. So looking at this, and we're starting when n equals 2. So if I look at n equals 2, let's just make sure our formula works. This would equal, we're plugging in 2 wherever we see an n. So this would equal a sub 2 minus 1 is a sub 1, plus 2 times 2 is 4, minus 1 is 3. My a sub 1 term is given. We said it was 3. And so if I plug in 3 there, I have 3 plus 3, which is giving me 6, which is our second term of our sequence. So far, so good. This is what we're thinking our sequence is. So now let's try it if we plug in 3 for n. So if I look at the third term, when n is equal to 3, I would have a sub 3 is equal to a sub 3 minus 1 plus 2 times n, so 2 times 3 minus 1. So simplifying this, I get a sub 2 plus 2 times 3 is 6. 6 minus 1 is 5. A sub 2, though, we found was 6. So rewriting a sub 2 as 6, we have 6 plus 5, which gives us our third term, which is 11. So it looks like we found the correct formula for the nth term of that sequence. Let's just show one more time. So if we had n is equal to 4, we're looking at a sub 4 is equal to a sub 4 minus 1 plus 2 times 4 minus 1. Well, this tells me I'm looking at the third term, plus 2 times 4 is 8. 8 minus 1 is 7. The third term we found was 11. 11 plus 7 is 18. Which, if we look at the fourth term of this sequence that is listed, we get back 18. So we did find the correct formula. A sub n is equal to the term right before it, and we can write that as a sub n minus 1 plus 2 times n minus 1. So in front of us, we have a formula. It's for factorial. In factorial, we can denote by n with an exclamation mark. We use this if n is greater than or equal to 0, so it has to be a positive integer. N is also an integer. 0 factorial is actually 1. 1 factorial is 1. If n is greater than or equal to 2, to get n factorial, you're going to look at n times the term or integer right before it, which is n minus 1, times the integer right before that, which we can denote as n minus 2, dot, 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 times 2 times 1. So if you were looking at 5 factorial, so 5 with an exclamation mark, this would be telling us that we're looking at 5 times 4 times 3 times 2 times 1. So I'm just going to go through and maybe group a couple of these and multiply. So 5 times 4, I know is 20, times this grouping of 3 times 2, I know is 6, times 1, I really don't need that times 1 there. So 20 times 6, that gives me back 120. So 5 factorial is equal to 120. If I were to look at 6 factorial, this is equal to 6 times 5 times 4 times 3 times 2 times 1. Well, we already did a lot of this work. Notice that 5 times 4 times 3 times 2 times 1, this is the same thing as 5 factorial. So really, this is 6 times 5 factorial. But we just found that 5 factorial over here was 120. So we really have 6 times 120. So 6 times 120, we get back 720. Another example, if you had n factorial, this is equal to n, and then it had parentheses, factorial. We'll notice kind of above what we just did, When I did 6 factorial, that was the same thing as 6 times the factorial right in front of it, 5 factorial. And I can write that as n minus 1 factorial. Okay, so let's go back to looking at some sequences. So looking at a recursive sequence. So a recursive sequence means that we're going to assign values for maybe a first term or maybe even a couple of the first terms in the sequence. And we're going to specify the nth term by a formula or an equation that involves the terms right before it. So we have the definition of a recursive sequence in front of us now. I pretty much just stated exactly what was in here, but let me just read it again. So another way to define a sequence is to write them down recursively. This means we assign a value to the first or the first few terms and specify the nth term by a formula or equation that involves one or more of the terms before it. So now we have an example here. We want to write down the first 5 terms of the following recursively defined sequence. So we have S of 1 is 5. So we know the first term of that sequence is 5. And then S of n is equal to 2 times S of n minus 1. So I already have the first term of my sequence. So now I'm looking for S of 2. So I'm going in here to this formula, and wherever I see an n, I'm going to plug it in this case, 2. So I have 2 times S of 2 minus 1. So this is 2 times S of 2 minus 1 is S of 1. S of 1 was given to us to be 5. So here we have 2 times 5. Let's see. So we're plugging in that 5 there. So we have 2 times 5, which is that 10. So looking at the third term, so S of 3, we're going back into our sequence wherever we see an n. This time we're plugging in 3. So this is equal to 2 times S of n minus 1. 3 minus 1. So this is 2 times S of 2. But we're given up here that S of 2 was, or we found was 10. So this gives us 2 times 10, which is 20. Our fourth term of the sequence, this is equal to 2 times S of 4 minus 1, which is 2 times S of 3. The third term of our sequence, though, we found to be 20. So let's write 20 in there. So 2 times 20 gives us 40. S of 5, same thing. Now we're going in and plugging in 5 wherever we see an n. So we have 2 times S of 5 minus 1, which is 2 times the fourth term, S of 4, which is 2 times this 40, which gives us 80. So if I was to write out the first 5 terms in the order, I would have 5, 10, 20, 40, 80. And then I'm going to put ... just to show that it's going on forever. Now that we know about sequences, let's talk about summations. So a lot of times in mathematics, we want to sum the maybe first n terms or n terms of a sequence. And that's where we get into what is called series. And series is a summation of terms of a sequence. So let me just read what is in front of us. So it says, oftentimes we want to find the sum of the first n terms of a sequence, a sub n. That is, we want to find a sub 1 plus a sub 2 plus a sub 3 plus dot, 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 up to a sub n plus a sub n. Rather than having to write down all the terms, we can denote using summation notation. So we're going to use the symbol, Greek symbol, that is called sigma. With that sigma notation, we're going to have k equals 1 below the sigma notation. We have n on top of that of a sub k, where we can define this k sub 1 on the bottom. This tells me what number I'm starting with for my integer, and this n on top tells me what integer I'm ending with. So the summation from k equals 1 to n of a sub k, this is equal to a sub 1 plus a sub 2 plus a sub 3, dot, 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 up to a sub n. So that, again, symbol, kind of a edgy E, is a Greek letter sigma, which is S in the alphabet. In mathematics, it means to sum or to add up the terms. The integer k is called the index of the sum. It tells you which term to start to sum up and which to end the sum. So that sigma notation with k equals 1 on the bottom and on the top of a sub k is an instruction to find the sum of the terms a sub k of the sequence of a sub n, starting with the first term and ending with the nth term. It is read as the sum of a sub k from k equals 1 to k equals n. So let's look at some examples of summations. So let's say that you have the summation starting with k equals 1 to n of k all over k plus 1. So it asked us to expand each sum. So first thing that we want to do is find the terms of this sequence. So technically, this a sub k is k all over k plus 1. So if I wanted to look at a sub 1, this is going to equal 1 all over 1 plus 1, which is 1 over 2. So far we would have 1/2 plus, we need to find the second term of the sequence. So plugging in 2 wherever we see a k in the formula, we have 2 all over 2 plus 1, which gives me 2 over 3. So this would be plus 2/3, the second term, plus the third term. So plugging in 3 wherever we see a k in our sequence, we would have 3 all over 3 plus 1, which is equal to 3/4. Plus dot, dot, dot. We're going to go 1 less than n. So I could write this as a sub n minus 1. So this would equal n minus 1 all over n minus 1 plus 1, which is n minus 1 all over, well, -1 plus 1 is 0, so we just have all over n. So plus n minus 1 all over n, plus the nth term, which would be n all over n plus 1. So we just expanded the sum of that sequence. So in our next example, we're given a sum of terms, and we want to express each using summation notation. So we need to come up with a formula for the nth term. So going through this, our first term, we have 1 over 1 quantity squared, plus the second term, which is 1 over 2 quantity squared, plus the third term, which is 1 over 3 quantity squared, plus 1 over 4 quantity squared, plus 1 over 5 quantity squared. So looking at this, let's start with k equals 1. K is in the denominator. So doing integers 1, 2, 3, 4, 5. So I'm ending when k is 5. Notice my numerator is always 1. And then I'm squaring this. So the summation of the sum of the sequence 1 over k quantity squared from 1 to 5 would give us this above. So looking at the next summation, trying to find the formula, we have 1 plus 3 plus 5 plus ... 2 to the n minus 1. So I notice here that this looks like these are odd numbers. So I have, starting, let's say k equals 1. And we're ending with 2 to the n minus 1. Well, let's just first look at this. So if we had 2 to the n minus 1, actually 2 to the k, and we plugged in our first term 1 for k, we would get 2 times 1 is 2, minus 1 is 1. So we get that first term. And k is 2. We get 2 times 2 is 4, minus 1 is 3. That gives me the second term of the sum. If I plug in 3, 2 times 3 is 6, minus 1 is 5. Gives me the third term. So that looks like it's right. And so I'm going to go until I get to 2 and minus 1. So that means that the last value I'm plugging in would be n. Plugged in n, we get 2 times n minus 1, which gives us this last term of the summation. So we found the formula for the sequence and the summation formula for that series. So we have properties and formulas of sequences. If a sub n and b sub n are two sequences and c is a real number, then we can say the following holds. So if we have a summation from k equals 1 to n of c times a sub k, this is equal to the same thing as taking our real number c, pulling it outside of the summation. We can look at c times the summation from k equals 1 to n of a sub k. The next piece of the formula, we have the summation k equals 1 to n, parentheses of a sub k plus b sub k. So we're looking at summing the terms of the sequence of a sub k and of b sub k. Doing so, or a sub n and b sub n, we can look at this as the summation k equals 1 to n of the first sequence a sub k plus the summation k equals 1 to n of the second sequence b sub k. So it doesn't matter if we have this plus here, we're going to add. If we have a minus in between the two sequence, we're going to do the same thing but subtract. So this would be this summation from k equals 1 to n of a sub k minus the summation from k equals 1 to n of b sub k. The next one we have the summation k equals j plus 1 to n of a sub k. So notice here, we're not starting necessarily here when k is equal to 1. And so if we want to start, let's say we want to start at the 5th term and add to the 10th term, what we would do is we're going to look at the summation from k equals 1 to n minus what we of our sequence a sub k minus what we don't want in there. Well, we don't want the terms from k equals 1 to j. So we're going to look at minus the terms k equals 1 to j of a sub k. So the next one, we have the summation k equals 1 to n of some constant c. So basically, I'm adding c n times. So this is just going to be equal to c times n. If I'm looking here at the summation from k equals 1 to n of k, there's a formula for this. So the formula for this is n all times n plus 1 all over 2. So if they have a k squared term as our sequence, summation from k equals 1 to n of k squared, our formula is going to be n all times n plus 1 all times 2n plus 1 all over 6. And the last one, if we were looking at the summation from k equals 1 to n of k cubed, then the formula to find the sum of those n terms is n all times n plus 1. And this is all over 2. And this whole quantity is squared. So we can use these properties to help us find the summation of terms. So looking at an example in front of us, we have the summation from k equals 1 to 10 of k squared minus k. So let's use these properties to find the sum of the sequence. And so looking at this, we can break this down. This is the same thing as the summation of k equals 1 to 10 of the first sequence k squared minus the summation k equals 1 to 10 of the second sequence, which is just k. So notice from our formula up here, our n value is equal to 10. And for the k squared, we're going to look at n times n plus 1 times 2 times n plus 1 all over 6. So using this formula, we have 10, again, all times 10 plus 1, all times 2n plus 1 all over 6. minus, so if I'm looking at the summation of k equals 1 to 10 of just k, then I'm going to use this formula up here. Again, n is 10, so I'm looking here at 10 all times 10 plus 1 all over 2. So let's simplify this. So this is 10 all times 11. 2 times 10 is 20. So 10 plus 1 gives us 21. So all times 21 all over 6 minus 10 times 10 plus 1, which is 11, all over 2. So 10 times 11, that's 100. And 10 times 21 all over 6 minus, let's reduce a little bit. 2 goes into 10 5 times. So I'm left with 5 times 11, which is 55. I'm going to reduce a little bit over here too. I noticed that 6 in my denominator, well, that has a 3. 3 goes into 6 twice, and 3 goes into 21 7 times. And then I noticed that I have 2 and 110. 2 goes into 2 once, and 2 goes into 110 55 times. So I'm left with 55 times 7. 7 times 5 is 35, carry my 3. 7 times 5 is 35, plus that 3 is 38. So I have 385 minus 55, which is equal to 330. So a lot faster if we have these formulas for these summations, instead of finding the first 10 terms and then summing those up. If we found those first 10 terms of the sequence and summed it up, we should get 330. The next example, we have the summation from k equals 5 to 12 of 3k cubed. So we're not starting at the first term. So let's look at this as summing from k equals 1 to 12 of 3k cubed minus, we don't want the first 4 terms. So minus the sequence or series from k equals 1 to 4 of 3k cubed. Recall we could bring that coefficient of 3 outside. So I could have 3 times, and I could factor that out of both of those. So 3 times of summation from k equals 1 to 12 of k cubed minus the summation from k equals 1 to 4 of k cubed. Well, there's a formula for k cubed, and our n value for the first one is 12, and for the second summation, n is 4. And recall the summation from k equals 1 to n of k cubed, that was all equal to n times n plus 1. That was all over 2, and then quantity squared. So we have 3 all times. So the first summation, k is 12. So we'll have 12 all times 12 plus 1 all over 2, quantity squared, minus n is 4. So we're going to have 4 all times 4 plus 1 all over 2, quantity is squared. And so now we can simplify. We have 3. Let's actually simplify. 2 goes into 12 6 times. So I'm going to be left here with 6 times 12 plus 1, which is 13. Minus, still going to have this 3. I can think of it as distributing. 3 all times this 4. But let's simplify. 2 goes into 4 twice. So times 2 times 4 plus 1, which is 5. Might be easier if we keep that 3 out front. Keeping that 3 out front, we have 6 times 13, which is 78, minus 2 times 5, which is 10. So we have 3 times 78 minus 10, which is 68. 3 times 68 is 204. So if we summed up the 5th term through the 12th term of that sequence 3k cubed, you should get back 204. So what we just talked about was our section 13.1 in our textbook, which talks about sequences as series. We'll create a new video to go over arithmetic and geometric sequences and series, so special sequences.